Hello, Stats class. Here's the lesson 11.1a notes, which is Introduction to a new type of test called a chi-squared test. So the situation we're going to be doing in chapter 11 is categorical data. And you might think we've already done categorical data, right? We did proportions. But what we're going to change in this chapter is we're going to allow there to be more than two categories, many categories, which you saw some of that in the warm-up already. Categories. And we're going to start off by comparing that distribution of the categories and the proportions of all of them, compare that distribution to a hypothetical distribution. And so we have a new test statistic that's called chi-squared. It looks like a fancy X, but it's the Greek letter chi. Actually, first I'll do this. It's our new test statistic. Instead of T or Z. So it's the Greek letter chi. Here's a silly joke for you. Some people like to pronounce it chi, and if it was chi, it would be a T test, not a chi-square test. Do you get it? It's pronounced chi, not chai. So chi-squared, the official formula, which also was introduced to you in the warm-up, is you add up a bunch of stuff, so that's the sum symbol, and the things you add up are the observed count for each category minus the expected count, and you square that and you divide by the expected count. And you did that in a table in the warm-up on Desmos. And the idea here is if the sum of all of these is very big, that means the observed are far from the expected. So if chi-squared comes out big, we have the data is very different from what's expected, which would be significant. And that would give us a small p-value, which would cause us to reject our null. And the null is going to be that the expected counts are approximately right. Reject the null hypothesis. The small chi-squared means that the data, the observed are close to the expected, so the data is similar to what we would expect. And that would cause us to have a large p-value, and we would not reject the null. So that's where we're headed. Significance tests for comparing distributions of categorical data. Crazy. So before I go on, I want to say over here that there is a way to do this on your calculator. I'm going to talk about the calculator shortcut for a bit. Some calculators have a goodness of fit shortcut, which we'll talk about later when we get to the official 4-step test. But for now, I just want to say, if you're doing this on your calculator, you're going to put your observed values in list 1. You're going to put your expected values in list 2. And then list 3 is where you're going to do this calculation. So I'm going to show you that just because it might help some people. I have some data from last year's M&M's experiment. And here's the observed and the expected. And then what you do is list 3, you go to the very top like I just did, and you tell it that you want it to do list 1 minus list 2 squared over list 2, which is basically the same as this. So over here on the top of list 3, I tell it I want parentheses list 1, that's second one, minus list 2 squared divided by list 2. And that's the magic formula that gives you chi-squared, because these contribution numbers get added up to get chi-squared. So chi-squared is the sum of list 3, which you could either add them up by hand, or easier is I'm going to go back to the home screen and go to second stat and math, And one of the options is sum. Isn't that convenient? And you can get the sum of list 3, and that's your chi-squared value. There are other ways to get it, but that is the first shortcut that I'm going to show you. You get to this by going to second stat and math. Maybe I should go a little further down. So that's the calculator method. There's another calculator method that I'll show you later, but it only works for some calculators. This works for all calculators, all graphing calculators. So before we go into the hypotheses, let's continue talking about this a little bit. The chi-squared distribution is not a normal curve type shape. Unlike T that's symmetric like normal curves, the chi-squared distribution is always skewed right. Looks like that. And it's always positive because we're squaring and dividing by a positive number. So this boundary over here is 0. Chi-squared is always a positive value, and it's significant or unusual if you're over here in the tail. This last 5% over here, that's my alpha usually, that's rare values of chi-squared. And this piece over here is not rare, or reasonably likely values over here. So if the data is reasonably close, the data is often reasonably close to expected count, but if it's way over here, that means something weird is happening. So it is a right-tailed test. That right-hand tail is the p-value that we're calculating. And we'll use our p-value the same way we've used them before to reject if you have it smaller than 5%. So that's what the graph looks like if you're looking at chi-squared and trying to do the calculations. That way you're going to mostly make the calculator do it. So for this first lesson, we're mostly writing hypotheses and finding a p-value and not doing the formal 4 steps yet, but let's talk about the hypotheses. The hypotheses can be written in either words or symbols based on what I set up above. So the null hypothesis is that everything is as we expected. So I'm going to use the M&Ms as an example here. The null hypothesis for the M&Ms is that the company's published proportions are correct. Or in other words, all the colors are the proportions that we expect them to be. The alternate is that at least one of those proportions is different. It wouldn't have to be all of them. So it wouldn't have to be all of them. It could be even just one of them, and then there's maybe a few others that are a little bit different, but not enough to make a difference, but there's one that's just off, right? So that's how you write them in words, and it's really common in this chapter to write your hypotheses in words, and that is just fine to do that. You do want to make sure you talk about the population, and so we're not talking about the sample has the right proportions. We're talking about the population. This should be the population color distribution, not the sample. Or you could do it in symbols. So if you're doing it in symbols, I actually think it's more of a bother this way because there's a lot of proportions here. With M&M's colors, there's 6 different colors. So you'd have to write one of these for every color. So you'd have to write the proportion of blue is 0.24 and the proportion of orange is 0.2 and all of that. Most of the time it's easier to say, look, here's a table and my null hypothesis is the table is correct rather than write them all out. So you could write, you'd have to write all 6 of them if you were doing this method. And then the alternate is that at least one of these is not the same. So it would be P blue is not equal to 24, or P orange is not equal to 0.2 or all the rest. And I personally prefer not to do it that way. I prefer to write the sentences, but at least one is different. You could write that in words if you wanted to. That's going to be a kind of a theme of this chapter, that at least one is different is almost always going to be our alternate. So our observed data, we've already talked about this a little bit, is the counts of each category, not the proportions. So we're talking about the sample data. And notice that it's not the proportions that we're worrying about. We're worrying about the counts. Our null hypothesis is about the counts. Expected values, we use those proportions that were in our null hypothesis to calculate them. So it's the given percentages from the null hypothesis times the sample size. So in other words, each E, or each expected value, is the sample size N times P, whichever one we're talking about. So if we're talking about the first category, it's N times P1. And then E2, which is our second expected count, comes from N times P2, and so on. You do that for all of them. So with the M&Ms data, I took my sample size of how many M&Ms it was, and multiplied by the 0.24 and the 0.2 and all the rest of them. That's how I got the expected counts. And then we already talked about how to get the test statistic. Then you use these to calculate the test statistic. Which we wrote that up above. And then to find your p-value, there is, as you probably would have guessed, there's a thing called chi-squared CDF. And you have chi-squared, and you have your 999 or something like that, and then we have DF. It looks a lot like the ones we've seen before. This chapter, DF is changing again, and DF is now the number of, not the sample size, excuse me, but the number of categories minus 1. So DF is no longer based on the sample size. Now it's based on the number of categories. And so you can do that with, I'll just continue the M&Ms example. So I'm going to use last year's data since I haven't done yet this year's data yet. I'm going to use the chi-squared that we got last year, which is the 11 point, actually, I think it's on my calculator still because that's what I used. Yeah. So this is my chi-square value if I'm using the 11.346 from the example I did up above, 999. There were 6 colors, and so I'm using 5 for my DF. 6 colors minus 1. And if I do that, chi-square CDF is in the same menu, second bars, that you're used to finding the CDFs, and it's down there at number 8. And I would do the answer that I just got, and 999 and 5. And it gives me 0.0449, which is significant. That's interesting. Not very far below 5%, but it's a little bit below 5%. So I'd write my conclusion the same way we've learned before. Since P is 0.0449 is less than 0.05, we reject the null hypothesis that the published distribution of colors is correct. And we could do some more analyzing to try and figure out which color was off and things like that. And that's in future lessons, we're going to do more of that. So we will continue this next week. Of course, and learn a whole lot more about this. This is just the introduction. We haven't really done the formal 4 steps yet. We've just talked about certain steps here and there. We haven't talked about conditions yet. We will get there. So just wait, and we'll talk about the formal 4 steps next week.